In this video, I'm going to be going through the Unit 1 practice test and kind of telling you all the stuff you need to know in order to do all the problems. So we're going to start here on the first skill, which is using tables to find limits. All right, so for this one, we're just given a table and we're going to find a limit expression that correlates with this table. So remember, with a limit, we're trying to get our x values close to something, and then our y values also, we want to be close to something. All right, so here, generally for these ones, we're looking in the middle. And if it's not in the middle, it might be like one off for the middle because we're kind of coming in from both directions towards a number. And think about what these numbers are getting close. We kind of start at 5 and 7 and work towards the middle. Well, between those, our x values are going to be 6. So our limit as x approaches 6 of this function. And then it's going to be equal to, we're doing the same thing with our y values. Whatever our y value is getting close to, as we get close to 6 in the middle. All right, they both start at 3 and they're getting smaller, and you can see these numbers right here are really close to 2. All right, so this is our limit expression. All right, as x approaches 6, our y values are equal to 2. All right, the only difference with this problem is now we're doing one-sided limits, so we're going to do the one-sided limits and then write the full limit expression. So again, looking right in the middle here, where our x value is getting close to, all right, -4 with a small decimal, -3 with a big decimal, all those are really close to -4. So we're going to be looking at the limit as x approaches -4 from the left, and the limit as x approaches -4 from the right. All right, so those are our two one-sided limits. And again, the way we figure out what these are equal to, for the left-hand limit, we only look over here. And as our x values get close to -4 that direction, our y values look like they're getting close to 10, right? 9.9 and then 9.99 are basically the same as 10. And then on the right side, as our x values get closer to -4 in that direction, our y values look like they're getting closer to 3. And so on the left-hand side, as we go towards the middle, our y values get close to 10. On the right-hand side, our y values get close to 3. And then we put these together, and we don't have the direction, we just have -4. And the basic thing you need to know is if these two numbers were the same, so these two numbers here, right, are answers. If those two numbers were the same, they would be the answer for this third one as well. But since they're different, every time they're different, that means our limit does not exist. All right, so this is how we use the one-sided limits to evaluate a full limit as well. On the back of the page, now we're just making our own tables to make something true. So we want our x values to get close to -2. So right in the middle here, we want things to be close to -2. I personally made this one negative because if you remember on our number line, we have -3, -2, -1. So the values are going to look a little bit bigger than 2 on the left. So like -2.001 is just to the left of -2, -2.01. And again, there's an infinite different ways you could tackle this problem in terms of what decimals you're using. But again, you should be close to -2, 5, and like -1. All right, in the middle there, and -2.001 and -1.99 are really close to -2. And we do the same thing with 4. All right, 4 is our traditional bigger numbers, certain numbers. Had to be close to 4. These ones don't have to be increasing like the x's one, so I could actually do like 4.001 here and 3.99 here. All right, as long as they're close to 4, and then like we get a little bit farther away from 4 as we go away. Again, there's no rhyme or reason as long as those values are getting closer to 4 as we work into the middle. All right, so that's one possible table, but there's an infinite number you could do. This table, same thing, except for now we have the one-sided limit. So the important thing is both of these limits have to do with 3. So in the middle of our table, we need our values to get close to 3. So +3, so I can just do something like this. Again, there's no specific reason I'm choosing these, as long as that they're getting closer to 3 as I get close to the middle, and now they're going to be slightly bigger than 3. Again, they're just getting bigger as I go to the right. You can kind of do however you want as long as they get close to 3 in the middle. And now we have left and right limits. On the left of 3, we want our values to get close to 4. So right here should be our value closest to 4. So we can do like 4.01. And as we get farther away, we can make the numbers a little bit bigger and farther away from 4. And it doesn't matter if they're increasing or decreasing or anything like that, as long as they're getting closer to 4 towards that middle line. And on the right-hand side of this, on our right-hand limit, we want to be close to -5. And it doesn't really matter if we're slightly above -5, slightly below -5. And again, you could always do something like this and just make them all -5. Right? If they're all -5, that means it's also close to -5. All right, so that's our first skill, using tables for limits. Our next skill is about using graphs for limits. It's very similar. This one requires a little bit less work because you're just looking at a graph. So here we're looking at -1 from the left. All right, so if I'm looking at -1 from the left, I go to -1 first, but I'm only looking to the left here, so in this general region. And if I'm only looking at those, I can see kind of as I approach -1, as I'm going towards -1, I get -6 as my limit, this dot here, basically. And then next I want to do -1 on the right, so I have -1. I'm just doing all this stuff on the right. And I see as I do that, as I kind of work my way towards -1, I'm going to go into this open circle here, which is at 2. And we've seen before that if these numbers are not the same, then the full limit always does not exist. This problem is literally the exact same. The only difference is they're both open circles instead of one open and one closed, but nothing's going to change. 4 from the left, I'm kind of on the left of 4 and working my way towards 4, and I get to that open circle, it's at 6. On the right, I work my way towards 4 from the right, and I go to that open circle, it's at 1. And they're not the same, so that does not exist. If these were both the same number, I'd write the same number for the third question as well. All right, more of the same on the back. All right, the limit at -5. Right, -5 is here. And I'm thinking about things that are around that value. So really you're focused on the lines and not the dots. And the lines are coming towards that open circle there, and that's at -2. All right, so that's our limit at -5. What about at -1? -1, with these two separate lines, one going down here and one up here as we get close to -1. And that's a jump. And we know when there's a jump in our graph, our limit does not exist. And the last one, 4, looks just like the one that we had at -5. We have these two sides that are going together and meeting at that open circle, and that open circle is at 0. All right, so again, don't worry so much about the circles and dots. You're more worried about the lines. So as the lines go close to those values, that's going to tell you where your limit is. Question 4, same thing. First one, limit as x approaches -2. -2 is down here. All right, my two directions come towards that line, and that's -6 at 0. All right, my two lines are going there, and this one is one of those that seems confusing because there's no circle or anything, but again, if you're more focused on the lines than the circles, they're both going there, and that's at -3. And lastly, at 7, on both sides of 7, we have these arrows going up, so that's going to infinity. That's just using graphs to find limits. All right, next up we have the limit rules to find limits. I'm going to try to get all this on the screen at the same time. All right, the limit rules basically say you can break up your limits into smaller parts. So if I have this limit here and I have a plus in the middle, I can break this up into 2 limits and separate it out into 2 separate problems. And then these values I have in the given information. The limit of f at 2 is 3. The limit at g of 2 is -2. And I add those together and I get 1. So this is just knowing that you can break your limits down into smaller pieces. This one I could break it up once with that minus sign. And then you can do another thing called the constant multiple. So now there's just a number in front of something. You can bring that in front of the limit. All right, and then when you do all that, now we have it down to just the limits that we have above. The limit as x approaches 3 is 5. As g approaches 3, it's 10. And I get -20 as my final answer. All right, and the last one is a division one, but again, division, as long as you're not dividing by 0, it's the same thing. So it's going to be being 3 limit as x approaches 5 of x. Make sure you keep this number the same. And I'm also going to have a limit on the bottom. plugging my values at 5, I get 0 for f and 4 for g. All right, and it's fine to have 0 on the top of a fraction, not the bottom, but on the top, that just gives me 0. All right, so this one's just knowing your limit rules and knowing you can break down this kind of complicated looking limit into smaller ones and just using that information provided. All right, this next one is no more complicated than the front sheet, the only difference being that you have the graphs where you have to find the values yourself rather than being given to them. So it's a little bit extra work, but this is more what they would do on the AP test. They wouldn't tell you the limits, they'd give you a graph or a table or something like that. But the idea is still the same. I can break this down into just the multiplication of separate limits. So I just find these two things separately. At 3, the limit for g is 3. Oh, sorry, f is 3. And then for g at 3, it is 2. So you get 3 times 2, and that is 6. All right, so this one's same thing you did on the front. You just have to do a little bit more work of using the graph to find the values. This one is very similar to one that was on the front. You can separate it out, put the constant multiples in front, separate it out over addition, and you get this is your limit expression. You can write the middle step that I wrote on the front sheet, or you can just go straight to this expression. And then this is 5. At negative 3, f is 5. At negative 3, g is 0 because it doesn't go anywhere. All right, this is just 25. And the last one, we have division again, so we can just separate this out. We have a limit on the top. And on the bottom, we're going to have a limit. We're going to bring that constant multiple out in front. All right. And now we just need those values. So at negative 5, the limit of f of x does not exist. The limit at g of x is negative 7. But if I don't have a limit that doesn't exist, this whole thing just does not exist. All right, there's no limit at negative 5 for f because there's a jump. All right, so this whole thing doesn't exist. You can't do the individual pieces if one piece doesn't work. All right, next we're going to be looking at limit notation with asymptotes. So really, this is just all about getting the infinity in the right place. So if we have a vertical asymptote, that's our kind of hint. Our x values are getting close to a number, and our y values are going to infinity. All right, so this is one option. You could also put negative infinity there. That's also a vertical asymptote. You could also put the left side of 5. You could also put the right side of 5. So there's a bunch of different ways you can write it, but as long as the number is here and the infinity is there, it's a vertical asymptote. And then horizontal, you're just flipping it. So again, the key is that your y value is equal to a number, so that's equal to something. And your x is going to infinity. All right, and here there's only one alternative, and that's putting a minus sign there. That should be an arrow. It looks like a plus sign, but that's an arrow. All right, so simple as that. Really, those first two questions are about just getting your infinity in the right place. All right, next we have this graph, and we want to write the limit expression for each vertical asymptote on the graph. Well, in this case, there's only one vertical asymptote, and that's here. All right, so and it just says write a limit expression. There's 3 different ones you could write, but the one I'm going to write is the limit as x approaches 5 of my function is infinity. So the full limit is infinity because both these arrows are going up. But again, there's some alternatives. You could do the left side of 5 is also infinity. The right side of 5 is also infinity. So that is either 3 separate answers you could write for this problem. And what about horizontal asymptotes? Horizontal asymptotes are when we're going to infinity on the outside, so these parts of my graph. So I'm going to have 2 different answers because there's 2 horizontal asymptotes. I'm going to have a limit going to negative infinity. I'm going to have a limit going to positive infinity. Going to negative infinity, that's when I'm going to the left of my graph. So here's where I'm leveling out, and that's at negative 5. Going to positive infinity, that's where I'm going to make these big x values here, and that's at 3. So again, making sure the infinity is in the right place for horizontal asymptotes. You're going to infinity, so you're going to the outsides of your graph, and your graph is leveling off at those y values. Next, we have algebraic manipulation for limits. So the important thing is that when you're dealing with algebra and limits, is always to plug in first. Right? Because if you plug in and you just get a number, that's your answer. So if I were to plug in -6 into this, I'm going to get 36 plus 6 minus 42, and that's 0. On the bottom, I'm going to get 36 minus 18, and that's 0. So on the top and bottom, I would get 0, and 0, 0 means there's something you can do algebraically to simplify your expression. And the way we're going to do that in this section, most likely, is factor. So let's see, multiply to 42 and get -1, it's going to be -7 and +6. On the bottom, multiply to -18 and add to 3, that's going to be +6 and -3. And your goal, because we started with 0 over 0, is for something to cancel. And this gives us our limit as x approaches -6 of x minus 7 over x minus 3. Again, you notice I'm writing the limit thing every single time because I haven't actually plugged anything in. I'm still trying to evaluate the limit. But now that I've canceled something out, now I'm going to plug in -6, and now I don't have to write the limit part anymore. And that's -13 over -9, which the negatives cancel and give me 13 over 9. All right, so just make sure you're comfortable with factoring, and you'll be good for this type of problem whenever you get 0 over 0 with these polynomials. As I mentioned before, the first thing you should always try to do with the limit is just plug it in. So I'm going to plug in 0. All the things go away, and I just get -5. That's all I have to do for this problem because I got a number. I didn't get 0 over 0 or something else weird. All right, another limit. Again, try to plug in first. 7 squared is 49. That's 0. Let's see, 49 minus 21 minus 28. That's also 0. So I get 0 on the top and bottom if I try to do the limit, which means I can factor it. Or which means I can cancel something out, and I'm going to do that by factoring. Multiply 28, add to -3 is... what is that? -7 and 4. And something should cancel out because we had 0 over 0. This gives me a new limit expression. X plus 7 on the top, x plus 4 on the bottom. And now that I plug in 7, I don't need to write the limit because that's the evaluating the limit part. I get 14 over 11. All right, same thing. Whenever you get 0 over 0, there's something you can do to simplify your problem. Right, next one, again, should always start off. It's going to save you a lot of time in the long run if you always start off by trying to plug in the values. So I'm going to plug in 1. 1 minus 2 over 1 plus 3, which is -1 over 4. And then you're done because you just got a value and you didn't get 0 over 0 or something else like that. And lastly, number 5. All right, if you try to plug in 5, you're going to get the square root of 16 minus 4. That's 0. 5 minus 5 is 0. So you get 0 over 0. All right, in this case, you can't factor it because it's not a quadratic or something you can factor. So this is the other one, and the main hint is that square root is you're going to use the conjugate. So I'm going to multiply this by x plus 11 plus 4 over the square root of x plus 11 plus 4. All right, the conjugate because here I have a minus sign, and there I have a plus sign. Okay. So on the top, I use the fact that if I take these two terms, these two conjugates, and multiply them, that's equal to the first thing squared minus the second thing squared. So the first thing squared is that square root is just going to go away. Then I'm going to subtract the second thing squared, which is 4. 4 squared is 16. At the bottom, I do not want to multiply because that's just going to be too complicated, and it's actually not going to help at all. I can do a little bit of simplifying on the top. By combining those like terms. And then you can see something cancels. And something should cancel because I got 0 over 0 originally. And so now I have 1 on the top because I canceled it out. On the bottom, I have this square root conjugate that I started with. But now I should be able to plug in 5. And I already saw that's the square root of 16 plus 4. Which is 4 plus 4, just 1/8. All right, so we get 1/8 for this problem. Really, there's no way of getting around it if this problem's on a problem like this is on the actual test, that square root's the dead giveaway that you're using the conjugate. All right, if it's not a square root, that means you could probably factor it and cancel something. All right, next skill is talking about continuity. So the first one is just knowing the definition. All right, you can't do this page at all if you don't know the definition, and that's like the starting point of all this. So there's 3 parts. And the first thing is you just have to be able to plug that value into your function. So f of a has to exist. I have to be able to plug it into the function. The second one is the calculus thing, the limit of that function exists. And so we need these things to actually exist to talk about them. And then once we know that they exist, we want them to be equal to each other. And so we basically just write 1 and 2 are equal to each other. All right, part 3 is not really possible without part 1 and 2. All right, they have to exist and talk about equality. All right, it's not possible to non-exist and be equal. All right, next we're going to talk about discontinuities. And again, the hint for talking about discontinuities is when do you lift up your pencil as you're drawing. So if I trace along, I have to lift up my pencil to draw that open circle and that dot. So this is going to be one discontinuity. I have to lift up my pencil to draw this open circle and jump up to there. So this is going to be another discontinuity. And then again, open circle, put that little dot. I had to lift up my pencil. So that's another discontinuity. And then I finish. All right, so my discontinuities are at x equals -5, x equals -1, and x equals 4. Right. I'd always kind of work backwards. So the first one I would do is, are there any infinite or asymptotic discontinuities? And there's no asymptotes here because there's no lines going up to infinity. All right, so the first one is, or sorry, there's no asymptotic ones. Then the next ones I would see, are there any jumps? All right, a jump is when I have to go from one line up to another, and there is a jump in this one. It's the -1. So this is a jump discontinuity. The other ones are not jumps because the two sides kind of connect, which makes them removable. All right, so when you just have a hole in the middle of a line like these ones, when it looks like that, that's a removable discontinuity. All right, so those are our 3 types. All right, 3 is similar to the last one, but you're just working on a table instead. So they asking it, is it continuous at 4? Well, first of all, we need to figure out what is f of 4. F of 4, when I plug in 4, I get 4. Next, I need to find the limit as x approaches 4. And sorry, I put f here, but this should be g. Oops, g. All right, so what's the limit? Again, with the limit, you don't care about right at 4. So if I kind of got rid of that and you said, what's the limit going to be? Well, as these get close to 4 in the middle, the y values are getting close to 2. And you can see that these things are not the same. One's 4, one's 2, so this is not continuous. The other way to say this is it's discontinuous. But that's about continuity, so that's fine. All right, so just find, again, that's the 2 parts of the definition. Find the function value, find the limit. If they're the same, it's continuous. If they're different, it's discontinuous. And question 4 is the same as question 2. All right, just where do I lift up my pencil? I have to lift my pencil to draw that dot, draw that dot, draw that dot. To separate these 2 arrows, I had to draw there. So I have 4 different discontinuities. All right, those values. We solve our discontinuities have a circle with lines coming out of it. It's removable. So these first 3 are all removable. In order to be a jump, it needs to be 2 separate lines versus just a dot out by itself. So they're all removable, none of them are jumps. And the last one, you have these 2 arrows going off to infinity, so that makes this one an infinite discontinuity. And lastly, we're looking at piecewise functions and continuities. The important thing is we don't want to have any jumps when we switch along our piecewise. We just want to make sure these 2 sides meet up in the middle where they switch. All right, so if we're talking about x equals 2, all right, where they switch over, we want the left-hand side, which should be 19 minus 3x squared. All right, we're going to plug in 2 because that's the value we want to get close to. 3 times 4. And we get 7. So when on the formal way I would write this is the limit as x approaches 2 from the left is 7. Now let's do the same thing for the right. On the right, 13 minus 3 times 2 is 6. That's 7. So the limit as x approaches 2 from the right is 7. All right, so here's the important part. I found those two limits. If I combine these, that means the full limit at 2 exists and is equal to 7. And that's the same as if I just plugged in 2, right? Because plugging in 2 is the same as what I just did here. And this means it is continuous. So yes. So yes, it is continuous. I'll write it a little bit neater in the next example. All right, but this is basically how you determine it's continuous. You look at the two sides, make sure they're the same. All right, so again, here's how I guess you should write it on the test a little bit nicer. So I'm going to look at same thing. This one's 2 is where the switch happens. All right, so on the left-hand side is when I'm plugging 2 into that function. So it's going to be 20 minus 2 times 2 squared, which is 20 minus 8, which is 12. All right, so the left-hand limit is 12. The right-hand limit is when I'm plugging 2 into the bottom function, 15 minus 2, and that's 13. All right, these two things are not equal, and that means the limit as x approaches 2 does not exist. And if that doesn't exist, that means this function is not continuous, right? Because the limit existing is part of being continuous. And the only thing I did wrong is all of these should be g's instead of f's, because it's the function g. All right, this is kind of the way I'd expect you to write on the test. You have your left-hand limit, you find the value. You have your right-hand limit, you find the value. If they're different, the full limit doesn't exist, so it's not continuous. All right, here's another example. All right, same thing. We're going to find our left-hand limit, in this case at 1 of h of x. To the left of 1 is when I'm slightly less than 1, so I'm going to plug it into 2 minus 3x. That's negative 1. Do the same thing with the right-hand limit. When I'm just to the right of 1, I'm slightly bigger than 1, so I'm plugging into the bottom one. I get negative 1. So these two things are equal, and that tells me that the limit as x approaches 1 is equal, and it's the same value. All right, now the next thing I have to check is, now I know the limit exists. What about, oops, that should be h of 1. What about the actual function value? When I'm equal to 1, my function says I get out 4. And these two things are not equal, so that means this is not continuous. So this one has a lot of parts. You have to do the left and right limits to figure out if your full limit exists. And it actually does in this case, but then it turns out that your function value is not equal to that limit, so it doesn't satisfy property 3 of continuity, so it's not continuous. All right, and the last one is this one where we have to find the value of k that makes it continuous. All right, so k is just some constant we don't know. The important thing is, when this switch happens at negative 4, we need these two things to line up. So I need k squared plus 3x to equal kx. And this looks impossible to solve because there's a k and an x, but again, we know the switch is happening at x equals negative 4. So I can say k squared plus 3 times negative 4. When the switch happens, which is exactly when x is negative 4, we need these things to line up. That's going to be k squared minus 12 equals minus 4k. And now you just have to remember how to solve this type of equation. All right, this is a quadratic equation because you have this squared. So the easiest way, in my opinion, to solve these is get everything on one side. So I'm going to add 4k to both sides. And then factor it. So we're looking for numbers that multiply to negative 12, add to 4. That is positive 6 and negative 2. And that tells me that answers are going to be k equals negative 6 and k equals positive 2. All right, so those are our solutions to this problem. Again, set them equal to each other. All right, that looks complicated because you have k and x, but x has to be negative 4 because that's where the switch happens. We're trying to make sure that those two line up and we don't have that jump. All right, so this is a quick overview of all the problems that are on the Unit 1 practice test. Again, the actual test will be very similar to this, so if you can go through here and understand everything that's in this video and do this practice test without your notes, then you're ready for the test.